It's game day, and the spectators are gathering at the stadium. They're here for a special game, an astronomically amazing game. Not the kind when players throw a ball across a field, but when the sun throws the moon's shadow across Earth.
I'm ready to see a solar eclipse, dude. I want to see it make the sky black and stuff.
It's the 20th of May, 2012, just a few hours before sunset.
I don't know about you, but I am super excited for this season.
Thousands of people show up at the University of Colorado's Folsom Stadium for what Space.com called the world's largest solar eclipse party.
We are now all in the Guinness Book of World Records as the largest eclipse crowd in history.
We just heard that they're going to have a get-together here at the campus, so we decided to come down and watch the eclipse because they're pretty uncommon, right? Yeah, this is her first eclipse, so, right?
Yeah.
Being here at Folsom Field.
But in Colorado, a site that promises to be spectacular, an annular solar eclipse, when the moon partially blocks the sun. Weather permitting, of course.
It's a little cloudy right now, so it's kind of disappointing, but it looks like it's going to clear up.
Catching the eclipse is now a game of hide and seek.
It looks like the clouds.
The atmosphere in the stadium hasn't dimmed.
Oh, I think it's a great opportunity. I'm really glad that the University of Colorado has put this together for us.
Finally, a break in the weather. The clouds give way.
With the binoculars.
And it looks like a bite has been taken out of the sun. Seen larger than life on Folsom's Jumbotron and streamed live on the internet. The image coming from just down the street from another part of campus where the public have also gathered.
Well, we just knew a bunch of stuff was going on about the eclipse today, and we thought we would check it out and see what's going on.
It's Astronomy Day at CU Boulder's Sommers-Bausch Observatory, and the public is invited to an open house.
We got to see the sun on the big telescope, didn't we, Imogene?
Yeah, we did.
And what I thought was really cool is looking at the little aiming system and seeing how close the moon is to the sun right now on the map and seeing how it's getting closer and closer, huh?
Uh-huh.
When most observatories are found far from cities, the Sommers-Bausch Observatory is right in the middle of Boulder.
I googled it and I knew there was a solar eclipse. I know it's usually CU Boulder. So I thought, okay, I'll come here. I really wanted to come see this because I like science, like physics. I didn't see it. I was in India. I came from India, and I really wish to see if I like it a day.
Originally founded only as a research facility, the Sommers-Bausch Observatory at CU Boulder has grown to become a teaching tool for students and the public. Hello, and welcome to CU Science Update. I'm your host, Katie LaSalle. Since the early days of CU, there have been astronomy classes. But the university didn't have a significant telescope until 1946, when the Bosch & Lomb Company gave CU a 10.5-inch refractor. Just one problem: CU didn't have an observatory. A donation from the estate of Mrs. Mamie Summers in memory of her husband Elmer made it possible to construct a facility that would house the telescope. The new building would be named the Sommers-Bausch Observatory, and it was dedicated on August 27, 1953 during the 89th meeting of the American Astronomical Society. Under the directorship of Dr. Walter Orr Roberts, the SBO was jointly owned by CU Boulder and the High Altitude Observatory of Harvard University, which already had offices at CU and an observatory in the Colorado mountains. As the years went by, the Sommers-Bausch Observatory gradually became more of a teaching tool. Back then, Astronomy was taught under the Department of Physics. By 1957, the Department of Astrogeophysics was founded, which later became known as the Department of Astrophysical and Planetary Sciences. Astronomy classes at CU grew in popularity. As classes increased in size, there was a strong feeling that the observatory could use additional facilities and a bigger telescope. In 1973, a 24-inch Cassegrain reflector was installed, purchased from the Boulder and Shivens Company. The original 10.5-inch telescope was moved next door into the lobby of the newly constructed Fisk Planetarium, minus its primary lens, which was removed and placed inside a solar telescope in the physics building. At the start of the 1980s, construction began on new additions to the observatory, and new telescopes were purchased. An 18-inch Cassegrain reflector and a 16-inch reflector. They were housed in the observatory's newly expanded observing deck, which included a roll-away roof. And the solar telescope at the physics department was installed at the open end of the observing deck, called a heliostat. This telescope tracks the sun and directs its light down a tube, which passes through the floor into a classroom directly below. The beam of sunlight ultimately converges to form an image of the sun, a safe way to view sunspots and the occasional eclipse.
Oh, well, my favorite telescope is definitely the heliostat, simply because I don't have to stay up late at night to use it.
Keith Gleason manages the day-by-day operations of the observatory.
Yeah, I like that view.
He also sets up classes and the open house events. His passion for science began when he was just a freckle-faced boy growing up on a farm in Oklahoma. After finishing a degree in physics at Oklahoma State University, Keith wasn't sure where to go from there. Then one year on his birthday, Keith's wife gave him a book, George Abel's Exploration of the Universe.
And it's the only textbook I have ever read from cover to cover, including the preface all the way to the very last page of the appendices, and I read it in 2 weeks. I went to work during the day and I came home at night. My wife went to bed at 10 o'clock and I read until 4 o'clock in the morning, and I did that for 2 weeks in a row. And when I finally closed the book, I said, that's what I want to be when I grow up. It addressed all the questions that I had on astronomy, answered many of them, and then the beauty of astronomy is there's still lots of questions that are unanswered. So I decided that's what I wanted to do, and I proceeded to apply to graduate schools in astronomy after that.
Keith's passion for astronomy is also shared by his colleague, Fabio Mezzalira.
As a young kid, I've always looked at the sun, I've always looked at the stars, and astronomy to me was really the place to be.
Today, he's a technician at the SBO. Fabio originally studied aviation and learned to become a pilot. But after a stint working in the IT industry, he decided that he was happiest doing astronomy.
But on the technical side, because I tend to be really good with my hands and with my head when it comes to, working through problems that machines tend to give us.
Fabio enrolled in astronomy classes at CU, and not long after, a staff position opened up at the observatory.
I got lucky, like some people do, and I managed to get hired at a real observatory, and this is where I plan to stay.
His pride and joy is working on the 24-inch telescope in the dome, which he calls Old Roy.
These 24-inch telescopes are built like tanks, so they're very well built, very heavily built.
Unfortunately, the company that built the telescope is no longer in business. With parts hard to come by, maintaining the telescope has become a challenge.
We gotta build parts, we gotta, these are unique. And this is what I love about astronomy, is that everything you touch in astronomy very much is one of a kind. And so I love immersing myself in trying to make it work and trying to build it, and then build it robust enough so that the students can actually use it.
Even the rotating dome roof is considered by the university to be just another piece of instrumentation that Fabio has to maintain. The dome shape is easily the most recognizable part of any observatory, an inverted bowl with a window to the stars. But long before telescopes were invented, observatories were often made of stone pillars that were aligned with the sun and certain stars. The most talked about is Stonehenge. Located in the British Isles, Stonehenge is composed of 900 rings of stone, probably put there by Neolithic farmers between 3000 and 2000 BCE. The stones may have been aligned with the sun and moon. But without written records, it's hard to tell whether Stonehenge was actually an observatory or a religious temple, or both. Another stone circle can be found in Egypt. This one is even older than Stonehenge. Nabta Playa is considered the world's oldest observatory, constructed some 6,000 years ago. The site consists of 5 megaliths, which are aligned with bright stars. That would have been significant to the nomadic cattle herders of the time. Ancient observatories can be found all over the world. These images were taken from GeoEye's Iconos satellite. They show the remnants of long-lost observatories built by ancient peoples in China, Cambodia, Peru, Chile, and Mexico. Closer to Colorado, the people who lived in the high desert of Chaco Canyon, New Mexico, were expert sky watchers, evidence of which lies in the ruins of elaborate stone buildings that appear to have been built along celestial alignments, and in a petroglyph found near the top of a butte, which dates roughly to 850 CE.
You do think of the individuals from thousands of years ago, and they putted around on their everyday mundane lives trying to survive. But occasionally, they would have an inspiration, and maybe what separates the human species from all the other species, they look up at the stars and say, I wonder what the heck those little points of light are, and wonder if they have meaning, and oh look, there's a few wanderers around there, we'll call them planets. I wonder if they have significance to us, which of course was the origins of astrology.
Ancient observatories helped turn the night sky into something that made sense. The periodic motions of stars and planets could easily be tracked, and these observations led to the production of accurate star charts for seafarers and for nomads crossing the desert. Many of the ancient astronomers constructed sophisticated sighting instruments, like the sextant, for determining the angular positions of stars and planets. They also kept meticulous astronomical records that were used for centuries. They also tried to explain the nature of the heavens and ask those eternal questions, like, why are we here?
What are we? How do we fit into the scheme of things? And I suppose we could live our entire lives and not ever know the answer, but we keep asking that same question, so obviously we must be interested.
Ancient people saw the universe with awe and superstition, but the earliest astronomers attempted to explain what they saw, and they came up with some remarkable theories. The 2nd century Greek astronomer Claudius Ptolemy saw the universe as a complex system of transparent spheres to which the stars and planets were attached, and they all revolved around Earth. The geocentric model of the universe could even be used to predict where the moon, planets, and sun would appear in the sky at future dates. Astronomers found this model to be so useful that it persisted for 1,500 years. But there was one thing the geocentric model couldn't explain. Every now and then, a planet would seem to suddenly stop and then reverse direction. The phenomenon, called retrograde motion, had always puzzled ancient astronomers. But what they didn't understand was that retrograde motion is actually an illusion. The Renaissance astronomer Nicholas Copernicus demonstrated that the retrograde motion of the planets could be explained better by a heliocentric or sun-centered universe. Copernicus showed that planets closest to the sun move faster, like cars on a racetrack. Therefore, Earth completes an orbit in a shorter time than planets farther out. Periodically, Earth's orbit overtakes that of the outer planets. From our point of view, they appear to stop and even reverse direction. As Earth's orbit swings past, the outer planet appears to resume its normal course. Although the heliocentric model provided a better explanation for the universe, it still wasn't widely accepted. But a 17th century invention would soon make the heliocentric model impossible to ignore. It began with a Dutch spectacle maker, Hans Lippershey, who is often credited for inventing what he called a looker. It was a telescope invented not for stargazing, but to modernize warfare. It wasn't until 1609 when the Italian astronomer Galileo Galilei turned the telescope skyward, and what he saw revolutionized astronomy. In his surviving sketches, mountains and valleys on the moon, satellites circling Jupiter, and more stars than have ever been seen before. Before telescopes, the only measurements of celestial objects were those that could be seen with the naked eye, but telescopes were now being used to find new celestial objects, such as asteroids and the planet Uranus. Fuzzy patches seen by the naked eye were revealed by telescopes as nebulous, clouds of dust and gas, many of which were found and catalogued by Charles Messier in the 18th century. The story of the universe was beginning to unfold. And this story is written in light. Light moves incredibly fast, 186,000 miles per second. Because light travels at a finite velocity, it takes time to travel across vast distances. The sun is 93 million miles away from Earth. Therefore, it takes sunlight roughly 8 minutes to reach our eyes. In other words, we see the sun as it appeared 8 minutes ago. If we were at Jupiter, we would see the sun as it appeared 35 minutes ago. And if we were riding along with the Voyager 1 probe, now more than 11 billion miles away on the outskirts of the solar system, the sun would appear as it did 15 hours ago. Voyager 1 and Voyager 2 have been traveling since 1977, and they will become the first man-made objects to enter interstellar space, the space between stars, where the distances are far greater. So great that astronomers had to come up with a new measuring stick, the light year, the distance that light travels in a year, or 6 trillion miles. Our galaxy, the Milky Way, is roughly 100,000 light years across. So we see the other side of the galaxy as it was when humans left Africa. There are objects so distant that the light now arriving to our eyes had been traveling since the time when dinosaurs walked the Earth.
The experience of putting your eye to an eyepiece and seeing something and know that that's real-life photons that were emitted by that distant object, well, it depends on how far away it was, maybe millions of years ago, maybe thousands of years ago, maybe only minutes ago, if it's something here in the solar system. But to know that those photons made that trip all the way across space, passed through the telescope and entered the eyepiece and then landed on the retina of your eye to give you that visual impression is to me, it's kind of thrilling. They made that trip just for me.
Telescopes use lenses that gather more light than the human eye can collect on its own. The light is then focused to make distant objects appear brighter. Refracting telescopes use 2 lenses to focus light. The largest is called the objective lens, and the smaller one is used in the eyepiece for viewing. Another type of telescope uses mirrors that point the light rays into the eyepiece. Hence, the name for this telescope is a reflector. Old Roy is a 24-inch Cassegrain reflector, which uses a secondary mirror and a hole in the middle of the primary mirror through which incoming light enters, a design attributed to Lauren Cassegrain, a 17th century Catholic priest and inventor. But in the 19th century, the new medium of photography would again revolutionize astronomy. Astronomers would no longer have to make sketches of their observations, because now they can just photograph the night sky. But to photograph distant and faint objects required long exposures and more light-gathering capabilities.
And so the key was, well, you need a bigger telescope. And the bigger telescope you have, or the bigger the lens, or the bigger the mirror, the more light-gathering power you get, so the fainter the object you can see.
The orbiting Hubble Space Telescope, launched in 1990, has looked farther than any telescope before. One of its greatest achievements shows objects so remote that they date back to a time when the universe began, over 13 billion years ago, and their light is just now arriving at Earth. This image shows distant galaxies that were formed near the cosmic dawn, when the universe was less than 3% its present age. Astronomers took the image over a 6-week period as part of the Hubble Deep Field Survey. These earliest galaxies appear as they were 350 to 600 million years after the Big Bang. Named after astronomer Edwin Hubble, the orbiting telescope takes us back to a time when stars may have first appeared in significant numbers, when the epoch of first light began. Today, our world is bathed in light. Visible light is described as a form of electromagnetic radiation, which is radiation we can see. The sun is a natural source for light. We perceive it as white light. But this light is made up of many colors, and we can see them in rainbows. Red, orange, yellow, green, blue, indigo, and violet. Water vapor from an afternoon rainstorm scatters sunlight, breaking it up into a spectrum of colors. We can make our own rainbows using prisms, a piece of glass or plastic with 2 or more surfaces through which light can be reflected or scattered. It was the English physicist Sir Isaac Newton who learned that when light passes through a prism, it gets split into different colors. Each color represents a different wavelength of light. We can demonstrate wavelengths by dropping a stone in a pond. Circular waves or ripples radiate from where the stone hits the water. A wavelength is the distance between the peaks or crests of the waves. Visible light has wavelengths of about 1/10 of a micrometer, so 10,000 wavelengths would be able to fit within the width of a dime. Light moves through space like the waves you see on the surface of a pond. But not only does it behave like a wave, light also behaves like a stream of tiny particles. Scientists call these particles photons. A photon is characterized by its energy, which depends on its wavelength. The higher the photon's energy, the shorter its wavelength. The lower the photon's energy, the longer its wavelength. In the visible spectrum of color, violet has the shortest wavelength, and thus its energy is higher than red, which has a longer wavelength. But color is determined by the way light interacts with an object. The apple is red because it absorbs all the wavelengths of sunlight except for red, which is reflected back into our eyes. Grass is green because all the wavelengths of sunlight are absorbed except green, which is reflected. If all of the wavelengths are absorbed, then no color will reach our eyes, and we will see black or an absence of color. But color can tell us more than what an object looks like. For objects that are very far away, like stars, color can tell us a great deal about them, what they're made of, their temperature and density, all without us ever having to go there. By separating the light into its different wavelengths, scientists have been able to observe the relationship between light intensity and wavelength. When we look at a rainbow, it comes as no surprise that the brightest region is yellow. That's because the sun emits mostly yellow light. A neon light, however, would produce a different set of colors. The electricity that passes through the tube causes the neon gas inside to glow. If we looked at its light through a prism, we would see only a few lines of color at specific wavelengths, creating a distinct pattern of emission lines that is unique to different substances. Scientists recognize this pattern as the emission spectra of neon. If we pass sunlight through the tube, then look at the sunlight through a prism, the familiar rainbow would be missing certain colors. That's because the neon gas has actually absorbed some of the sunlight. At certain wavelengths, the light intensity dips, creating a pattern of dark bands called absorption lines. Every element in every chemical compound has its own unique pattern of emission and absorption lines, which scientists use like fingerprints to identify the presence of a given chemical element. The study of these spectral lines is called spectroscopy, which enables astronomers to learn about the properties of distant objects, their chemical composition, densities, temperature, and whether an object is moving towards or away from us.
It gives you the answers of what's out there because we can't go there ourselves to scoop up a piece of a star and bring it back into the laboratory and analyze it. For example, the sun is largely a big ball of hydrogen gas. How do we know that? Well, we've never gone there. We've never scooped up a piece of the sun. But the spectrum that comes to us in the form of sunlight can be spread out, and you can easily see, there's hydrogen gas in the outer atmosphere of the sun, as long as with all of the other elements. So this is how we know, and this is actually one of the most important findings of astronomy. It's the support of the basic tenets of science is that everything is the same everywhere. In other words, the same laws of physics are the same out there as they are here. If that were not so, if we had laws of physics that we could conduct experiments here in the laboratory or here on the Earth, and yet we couldn't extrapolate that out to the sky, then our knowledge base would be strictly confined to the Earth and the atmosphere they're in. And we wouldn't, we would never be able to answer the question, what is a star? Because they would just be little points of light. So it's a huge advance in humanity to realize that we can deduce information about things that are billions of light years away, if you will, and never actually go there.
The color of light can also help us answer that question first posed by the ancients. Are there planets circling other stars? Missions like the Kepler spacecraft and the HARPS instrument at the European Southern Observatory in Chile have looked for tiny signs in the light from stars to tell us if there are any exoplanets out there. A large planet's gravity will cause its parent star to move in a small orbit, which causes subtle changes in the star's color. When the star moves slightly away from Earth, the light shows up as more red. When the star moves toward Earth, the light shows up as more blue. Astronomers explain this color shift as the result of the Doppler effect, first proposed by Austrian physicist Christian Doppler in 1842. He noted changes in the frequency of sound waves to an observer moving relative to its source. When the source moves toward the observer, the waves are compressed and take less time to reach the observer. The frequency of the sound is higher. But when the source is moving away, the waves are stretched, thus lowering the frequency. In the case of light, the spectra of an approaching object has a higher frequency and is shifted toward the blue end of the spectrum. A receding object exhibits a red shift. With careful measurements of red and blue shifts, astronomers have been able to show that planets are whipping around other stars. So far, more than 800 exoplanets have been found, with the hope someday soon to find an Earth twin. But the red shift and blue shift of light also tell us that the universe is growing. Early in the 20th century, Hubble and other astronomers made the first measurements of redshifts and blue shifts of galaxies. They realized that almost all of the light from distant galaxies is redshifted, and the farther away the galaxy, the more it is redshifted. Everywhere we look, galaxies are moving away from us, and the farther ones are moving faster. Studying light tells us that the universe is uniformly expanding everywhere, which is one of the core ideas that supports the Big Bang Theory, the model that describes how the universe began, from an extremely dense state to one which expanded rapidly. And we know this from what light can tell us. Visible light is only a tiny part of a much larger spectrum, much of which we can't see with our eyes. Beyond the violet is the ultraviolet. This light has shorter wavelengths and is more energetic. It's the light that gives us sunburns. Beyond that are the more highly energetic and dangerous X-rays and gamma rays. On the other side of the spectrum, beyond the red, lies the infrared, which can be felt as heat on the skin. This is followed by microwave radiation, and then finally, radio waves.
The astronomer Carl Sagan made it his life's work to engage the public in the world of science.
Ever listen to AM radio during a thunderstorm? The crackling sound you hear are radio emissions coming from lightning. When you see the flash of the lightning bolt, you also hear the crackle on the radio at the same time. That's because light and radio waves travel at the same speed, the speed of light. Not every lightning bolt is visible. Some are high up in the thundercloud or in another storm miles away. But you can still hear it on the radio, which make AM radios excellent lightning detectors. Visible light and radio are fundamentally the same. They are both composed of photons. The difference is the amount of energy they carry. In the electromagnetic spectrum, radio waves have the longest wavelengths, some as long as a mile. Any wavelength greater than 1 millimeter is considered a radio wave. Planets, stars, galaxies, clouds of gas and dust all emit radiation at many different wavelengths. When we combine these multiple wavelengths, the visible spectrum, X-rays, and radio waves, we can get a more complete picture of the universe. This popping sound is a recording of lightning, not from Earth, but from Saturn. Radio emissions from space were first detected in the 1930s. And large-scale building of radio observatories didn't take place until the 1950s. Many of these observatories used single-dish telescopes that had large parabolic surfaces. One of the oldest is the Level Radio Telescope at Jodrell Bank Observatory in Britain, which has been probing for radio emissions from the farthest reaches of space since 1957. Its single dish collects radio waves from space by bouncing them off a reflective surface, where they are concentrated on a receiver. The radio waves are then converted into electrical signals, which are amplified by computers. The world's largest and most powerful radio telescope sits in a natural depression in Arecibo, Puerto Rico. This huge 1,000-foot reflector is covered in almost 40,000 perforated aluminum panels. Suspended high above is a 900-ton platform containing various radio receivers and antennas, each tuned to a very narrow band of frequencies. Another of the world's premier radio observatories lies 50 miles outside of Socorro, New Mexico. The very large array consists of 27 radio dishes configured in a Y shape. The data from each 25-meter dish is combined electronically to give the equivalent resolution of an antenna that is 22 miles across. But there's one radio telescope that's become something of a celebrity in the public eye. Located in Parkes, Australia, it was made famous for its role in the Apollo 11 mission, broadcasting the live television transmission of the first ever moonwalk to 600 million people, or 1/5 of humanity, a story that was made into one of Australia's highest grossing movies. CU Science Update reporter Chelsea Linnell tells us more about a radio telescope known simply as the Dish.
Parkes Australia had the only dish on Earth capable of broadcasting the moonwalk.
Huh?
The moonwalk.
Oh. What's it doing in the middle of a sheep paddock?
Never had a mission of this importance fallen to a more unlikely group of local officials
Major McIntyre!
and engineers.
Constructed in 1961, the Parkes Radio Telescope in New South Wales is operated by Australia's National Science Agency, CSIRO, the Commonwealth Scientific and Industrial Research Organisation. John Sarkeesian is the operations scientist at the Parkes Radio Observatory. He first came to Parkes in 1996 to support the Galileo mission to Jupiter. Today, his job is to oversee the observatory's operation and systems development.
You know, people often ask, what's it doing in the middle of nowhere, here in the sheep paddock? Well, it may well be in the middle of nowhere, but in many ways, the telescope is at the epicenter of world radio astronomy.
At 210 feet in diameter, the dish is sensitive enough to detect a mobile phone signal all the way from Pluto. Capable of operating 24 hours a day, this radio telescope looks at a variety of astronomical objects.
The center of the galaxy passes directly overhead from our location, and so the richest and most interesting parts of the galaxy are very easily accessible from this location, and so we're able to study the galaxy in great depth from here, and of course make great discoveries and so on.
The single dish design is also ideal for tracking weak radio signals all the way from spacecraft. In fact, many of NASA's deep space tracking antennas were modeled after the Parkes telescope.
When people see our telescope, they think it's a satellite tracking station. They always ask, what's that satellite tracking antenna doing in the farm fields here?
Occasionally, NASA calls upon the Parkes telescope to help track their spacecraft.
That only represents a very small part of what we do, less than 1%. But they're invariably the most famous things that we do, and so people think that's all we do.
10, 9, ignition.
The most famous example is the Apollo 11 mission.
5, 4, 3, 2, 1, 0. All engines running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
In July 1969, astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins launched from Cape Canaveral, Florida on humanity's first attempt to land a man on the moon.
Eagle, Houston, we see you on the steerable, over.
Roger, Eagle, I'm done.
Roger, how does it look?
Eagle has wings.
Roger.
Television transmissions of the moonwalk would be relayed by the Parkes Radio Telescope to TV sets around the world.
Go! Capcom, we're go for landing. Altitude 4.
But the transmission almost didn't happen.
Tranquility Base here. The Eagle has landed.
Armstrong decided to walk earlier than planned.
Okay, Neil, we can see you coming down the ladder now.
The moon wasn't high enough in the sky for Parkes to receive the signal. That wasn't the only problem.
There was a severe windstorm that had struck the telescope just minutes before the moon was to rise here.
A safe wind speed for the telescope was considered to be 25 kilometers per hour. But during the moonwalk, the observatory clocked its most powerful winds ever.
So the tower that we're in here was actually shuddering and swaying from the onslaught because the dish was fully tipped over at its most vulnerable, waiting for the moon to rise when the winds of over 110 kilometers an hour struck the telescope.
The observatory's director, John Bolton, held his nerve and told the engineers to stay on it. Once the moon moved within the telescope's field of view, Buzz Aldrin switched on the TV cameras. NASA alternated between signals at 2 other stations, searching for the best quality images. But when they switched to Parkes, the pictures were so good that NASA stayed with them for the rest of the 2.5-hour broadcast.
It's one small step for man, one giant leap for mankind.
Ignition flight.
Following Apollo 11, Parkes tracked other missions, including the ill-fated Apollo 13, which suffered a loss of power after an explosion on the spacecraft.
Okay, Houston, we've had a problem here. We've had a main B bus undervolt.
The Parkes radio telescope was instrumental in picking up the faint radio transmissions, which helped save the mission from disaster.
Odyssey, Houston, we show you on the mains. It really looks great.
In the 1980s, Parkes was the main tracking station for the European Space Agency's Giotto spacecraft, which flew past Comet Halley in 1986. Before the decade was out, Parkes tracked Voyager 2's historic encounters with Uranus and Neptune. In 1996, the radio telescope tracked the Galileo spacecraft to Jupiter 10 hours a day for a full year. The remainder of the day was given over to radio astronomy. To track spacecraft and do radio astronomy at the same time, the dish was upgraded with a new dual-purpose focus cabin. Today, the Parkes dish looks very similar to the way it looked 50 years ago, but it's at least 10,000 times more sensitive. Thanks to upgrades, the dish remains a world-class instrument at the forefront of radio astronomy. It serves more than 400 astronomers from more than 20 countries each year. Astronomers like David Champion, who arrived from Germany to do a series of observations about pulsars, the rapidly rotating cores of massive stars that have reached the end of their life cycle. These objects are very dense and very small, some measuring no more than 20 kilometers in diameter, about the size of a large city on Earth. As these stars rotate, radio waves emitted from the poles sweep out across space. If Earth happens to be in the path of the beam, we detect a pulse of energy, hence the name pulsar. They are primarily a radio source, and pulsars were first discovered at the radio end of the spectrum.
We can see them at all kinds of wavelengths, but in the radio we are able to time them extremely accurately by looking at their individual pulsations that come from these pulsars, and then we know that in between each pulse there must be a full number of rotations of that pulsar. It's like looking at a lighthouse and seeing every flash of that lighthouse, and every time you see a flash you know it's been around exactly one time. So by doing the same thing with a pulsar, we can measure extremely accurate things to do with the orbit of the pulsar, the rotation of the pulsar, and also the orbit of the Earth and the solar system we're in.
When pulsars were first discovered in the 1960s, they were called LGMs, for little green men. The regularity of their pulses suggested an artificially produced signal. But that thought was quickly put to rest by the discovery of more pulsars. The Parkes radio telescope has discovered more pulsars than all other radio telescopes in the world combined.
Parkes is one of the best pulsar instruments there are in the world. It has a brilliant location being in the southern hemisphere. We see most of the galaxy from here. It's also far away from many of the population centers, so the interference from radio sources is far reduced compared to North America and Europe. It might be 50 years old, but everything about the telescope has been kept up to date and kept in the best possible condition, continuously revised and improved, and it's doing the best work it's ever done in its life now. It's as good as it's ever been, at its best already. So it's an amazing instrument.
Well, when I was a schoolboy many years ago, on the cover of my mathematics textbook was a painting of the Parkes radio telescope. And I remember sitting there in class in year 9 at school, daydreaming about working at an observatory like that thing. Not necessarily at Parkes, but at an observatory like that. So all these years later, to actually find myself working here really is very satisfying. It's satisfying. Right, that little dream did come true.
Thanks to its superb engineering and upgrades, the dish can look forward to making even more complex scientific observations in the years to come, and to more exciting discoveries in the future. Reporting for CU Science Update, I'm Chelsea Linnell.
It's June 5th, a couple of weeks after the annular eclipse, and the Summersbosch Observatory is having yet another open house.
Back in business again.
This time, the public has come to see a celestial event even more rare than the eclipse. They have come to see the transit of Venus across the face of the sun. The transit will be visible anywhere in the world where the sun is up, assuming, once again, that the clouds cooperate.
Don't ever do it without filters.
Oh yeah, this is neutral white, but it's much brighter.
This will be our last chance to see a transit with Venus before the next one, in another 105 years. The clouds break just enough to reveal a stunning view.
You see it? So cool. That is very, very cool.
That black dot crossing the northern face of the sun is the planet Venus, Earth's sister planet, the second rock from the sun.
Have you looked in it lately?
Middle of it.
Beautiful. There you go.
Thank you.
These transits are seen in pairs, 8 years apart. The last was seen in 2004. The German astronomer Johannes Kepler was the first to predict these transits. One would happen in 1631 and the other in 1639. Sadly, Kepler died in 1630 before he could see it himself. The English astronomer Jeremiah Horrocks was the first to record observations of the 1639 transit. Back then, only a few people with the right instruments were able to witness these transits. They didn't become big news until the 18th century. Scientific teams were sent across the world to see the transits of 1761 and 1769. The 1874 and 1882 transits were mentioned on the front pages of many newspapers. Thousands more people saw these transits. Back in 1716, Sir Edmund Halley understood that the Venus transits could be used to measure the true distance between Earth and the Sun. All it takes is measuring the time of the transits and doing the math.
Who would have thought that a transit of Venus would give us the distance to the Sun? I mean, obviously, it took a very brilliant mind like Sir Edmund Halley to come up with the scenario, but this is down-to-earth, practical, observational science. We just observe what's happening in the sky, think rather carefully on it, perhaps have to apply a little bit of mathematics and geometry to it, but in the end, you come away from it and say, I understand my place in the universe a whole lot better than I did before because I've taken this step to try to figure out things and not just wave my hand and say, it's magic, you know, it's inexplicable. It's up there in the heavens, and up in the heavens we can't possibly, you know, put our minds to things.
Modern astronomy has evolved to where the actual observing now uses sophisticated digital cameras attached to telescopes. And these cameras have become so inexpensive that even amateur astronomers can take some pretty amazing shots.
That these people are always making new discoveries of comets, of asteroids and stuff like that. It's just wonderful to see them involved with smaller telescopes and still going pretty deep because they take these telescopes out in the middle of nowhere and they can go really faint with these cameras.
But to get at the really faint objects, sometimes observatories have to deal with the seen conditions, an expression used by astronomers when they refer to atmospheric turbulence, which can cause stars to twinkle and sometimes make distant objects appear to go fuzzy. Some observatories can mitigate these conditions by getting above much of the turbulence and even away from light pollution. Observatories like the ones on Mauna Kea in Hawaii. Or you can get the telescopes even higher by launching them into space, like Hubble. But observatories like the Sommers-Bausch Observatory in Boulder can still give those who love astronomy a truly hands-on experience.
We have evolved to probably the best facility in the nation for undergraduate access to telescopes during their undergraduate program. I mean, there's not very many other places in the world where an undergraduate student can take an astronomy course and then walk halfway across the block, from Kittredge Commons, and actually come in and observe the stars. I mean, you don't have to go all the way up to the top of the mountain to do that. You just walk across the street.
These buildings are very unique, and they serve, of course, what I believe a very important function, because astronomy is a pretty big science. I mean, big, you know, you got to think big in order to really learn astronomy.
Where is the moon in its phase right now so that it's going to be a solar eclipse? This one? Yeah. Yeah.
The goal, of course, is if we can have young kids learn to appreciate science at an early age, then ultimately that supports our program in the end, 20 years later when they grow up. And it also, I think, helps the world in general because of supporting, of getting rid of the science phobia that is quite prevalent in today's world. And so we'd like to make people as excited about science and astronomy as we are.
I liked seeing Saturn because I've never really seen Saturn but in the pictures, so that was really cool. I just like seeing all the different stars and how they were made and how far away they are.
I'd like to study the science of like the sky, because you look up at the sky and then it looks like it's just a sky that never ends.
I will say that one of the most interesting revelations that occurred to me many years ago was when I finally came to the realization that I'm star stuff, that I am actually made out of material that wasn't always here, that was formed a few billion years ago at some other location in the universe within some other stellar system inside of a star that went supernova. And in the process of going supernova, created the heavy elements out of which mostly I'm made. I mean, discount the hydrogen that makes up the water that my body is made out of largely, but the calcium, the iron, the oxygen, all of those other potassium, all of the other minerals that your body is made out of, they didn't exist at the beginnings of the universe. They had to be manufactured in a distant star. Then ultimately its guts got exploded into space, to be graphic about it, and then get assimilated into another star, which probably then also exploded, which then got assimilated into a third star or a stellar system that we now call the Sun, and coalesced to form the Earth. So really, we're standing on solid ground when you stand on the Earth, the residue of old explosions from supernova explosions. So to me, that connection, to know that I and you and everybody is related to something that happened billions of years ago and in some other place in the universe, or otherwise we would not exist. To me, that's exciting. I think that's a lot of fun.
Astronomy is the only science where you can't perform experiments directly. You can't weigh stars and planets, touch or even smell them. But astronomers can observe the light, which tells so many stories. For CU Science Update, I'm Katie LaSalle.